by Luis Enrique Ramirez. I'm happy to introduce him, and he will talk about simple subquotients of relation modules.
Okay, good morning. Thank you for the introduction, and also thank you for the invitation. It's my second time in ICTP, and it's good to be back. Okay, so this talk will be about modules for GLN. So, and at the end, I will describe the subquotients of these kinds of modules. And the first thing I wanted to do is to describe or to construct relation modules, then show nice properties about these modules, and after that, at the end of the talk, I will discuss the simple subquotients. Okay, so during the talk, I will fix this N. GLN is the algebra of N by N matrices, and just this convention, I don't remember if I use it, but in case I have two complex numbers and I write this, that means that the difference is just an integer, a non-negative integer. Okay, and okay, so in order to construct this or describe the construction of relation modules, I want to give like the intuition. Where did these modules came from? And the intuition came from simple finite dimensional modules. So any simple finite dimensional module for GLN has a nice construction. In this case, the construction depends on certain elements called Gelfan set in Tableau, and a nice action on this Gelfan set in Tableau. So I will just write some of the ingredients here that I will use during the talk. So like, okay. Okay, so this Gelfan set in Tableau, the entries are complex numbers, and the important for finite dimensional modules are those satisfying these conditions, these two conditions. So what we are asking is differences between consecutive rows should satisfy some integral relation. Okay, so it's like going down should be greater or equal to 0, and going up should be greater than 0. So this is another ingredient, some conditions. And just a very fast recall about this Gelfan setting construction. They were able to describe all simple finite dimensional representation or finite dimensional model for GLN, and the construction is quite nice actually. They use the set of all Gelfan set in Tableau with this particular, so they consider some shift of the highest weight vector, and after this shift, they consider all Gelfan set in Tableau satisfying the previous conditions on the entries. This, okay, so we have some vector space generated by Tableau. This is another ingredient. Okay, so in this case, this finite dimensional model can be described as the vector space involved is the set of all these tableaux satisfying these relations or these conditions, this is the basis of a C vector space, and then the action is given by what is called the Gelfan setting formula. So you have this, the first time I saw them, they look quite complicated, but I just want to show this because the only relevant thing for me right now about these formulas is numerators here are given by a difference between consecutive rows, and denominators here are given by differences between elements of the same row. This is kind of the important thing I will use in the future today. So we have description of any finite dimensional module with this particular formulas. So it's quite nice theorem. Okay, so the question here that actually allow us to construct these relation models is the following. Is it possible to change a little bit or a lot these conditions on the entries in order to obtain a module structure on certain vector space generated by Tableau? So can we change a little bit the conditions? If we change a little bit the conditions, do we have still the same structure of GLN model using, this is important here, we want to use the same Gelfan setting formulas in order to obtain new models. Okay, so this problem actually is didn't come from anywhere. Just it was studied before, like Gelfan and Graeb studied this. They tried to construct or exchange a little bit the conditions in order to obtain new infinite dimensional models, and they did it for GL3 and GL4. They conjecture some construction of different models for GLN, but at some point, Lemire and Patera studied this paper, and then they realized that some of the constructions here were wrong, and what they did was they conjecture what should change in the construction here in order to obtain this kind of nice models to preserve the structure. Then, after that, some time passed, and Mazurchuk, he gave different constructions of models using different conditions on the entries of the Tableau. So some people work on this for some time, but there was not a concrete construction like for all possible changes you can do on the set of conditions in order to obtain a model structure. So those are examples of nice constructions. Okay, so what we did here, is try to study, first of all, we try to study the kind of conditions or the space of conditions we can impose on the entries in order to have these finite dimensional modules include, and all known families that I discussed here. Okay, so what we do is just we consider this set. It looks weird, but actually this is kind of a set of arrows. If you look at, okay, if you have this set of relations, you have the set of vertices. Okay, yes, that will be important. Maybe it's good to. So you have set of vertices for 1, for 2, for 3. So you have this set of vertices. Inside this, for this set of vertices, you define some relation. So it's a subset of B times B. And this relation, you can think about these relations like arrows. But the correct way of thinking is if you have a subset of this R, you can associate a graph. And the graph is very natural graph. Like you have an arrow going from ij to rs if ij rs is an element of the set of relations. So it's quite it's better to see these sets of relations as arrows. So in the case, I define some set like R plus. It's actually the set of all possible arrows going down between consecutive rows. Okay? And then this R minus is just the set of all arrows going up between consecutive arrows. That's the best way to think about these sets of relations. Okay, and okay, so from the ingredients of simple finite dimensional models, this Gelfan setting construction, the thing is we need certain Tableau such that the entries, the differences between the entries are integers, right? So this that will be like Tableau satisfying a set of relations. So the idea is we consider a Tableau with complex entries, and what we want for this Tableau with complex entries is like you have a set of relations or a graph. So the idea is you need that the differences should be like positive integers if the arrow is going down, or horizontal, and the integer the difference is positive if the arrow is going up. Okay, so just wow. Okay, just an example here. So you have this Tableau. What does it mean that this Tableau satisfies this set of relations or this graph? That means that this difference, so arrows going down the difference should be greater or equal to 0, an integer greater or equal to 0, and arrows going up should be an integer, a positive integer. So in particular, this Tableau satisfies this set of relations, and also this Tableau may satisfy this set of relations, the associated with the set, the empty set, just because you don't have any arrow to check if it is enough. Okay, but then if you just impose, or you just define the concept of a Tableau satisfying a set of relations, this is not enough. We can, so actually this is the example. We can have some entries that are equal. And if our goal is to use Gelfan setting formulas, that will not be allowed. Because in Gelfan setting formulas, I just wanted to remember, remind you, in Gelfan setting formulas, denominators are exactly differences between elements of the same row. Okay, so you may have that this Tableau satisfy certain sets of relations, but this is not enough. We need something else in order to have a hope in order to construct models. So first, I go back here a little bit. So if you have a Tableau that satisfies certain set of relations, we can construct. So this is, in order to construct this, the vector space or the basis of Tableau, it's okay just to impose the condition that the Tableau satisfies the sets of relations. So just let me just write here. We have this BC of T of L. That can be like this plus something that. Okay, so what is in this picture is kind of the definition of this set of Tableau. What should be the nice set of Tableau? In the finite dimensional case, we had this standard set of relations. In this case, what we consider is you have a Tableau, you consider all integral shifts of this Tableau, but leaving the top row fixed, and that will be a huge lattice of Tableau, but you need also, okay. Okay, the pointer, okay. You need also that all the Tableau here should satisfy the set of relations. At least they should be related with the graph or the set of relations, okay? And after that, we construct this, this vector space of and okay, so the question is, now we have a vector space and the basis is a set of Tableau. The question is it possible to endow this vector space with a GLN structure, GLN model structure, in order to get models, nice models? So first of all, we need to refine the concept of satisfying a set of relations, because of this stupid thing, this is allowed, so satisfying is not enough. So we need this concept. This concept is a Tableau is a serialization. So these first two conditions says that the Tableau satisfies the set of relations, so it's quite related with the graph associated with the set of relations. And the third condition says that you don't have integral differences between elements in different components of the graph here. Here you should consider the graph without arrows, like an undirected graph. And then you look at the connected components of this graph, and you should have this condition. So the difference should not be integer if you are in different connected components. So this kind of condition is better in order to at least guarantee that you don't have these singularities or these equalities inside the basis. Okay, so this is an example. So I just change 2 by square root of 2. And this is an example of a Tableau that is a serialization for this set of relations and also for this one. So you just check this, and the only condition, the additional condition you are imposing is that if you have 2 entries in the same row and they belong to different connected components, so the difference should not be integer. So you have this and this in different connected components, the difference should not be integer, and this is satisfied, okay? And just one small thing here is k is not anything. So you should have that this k, it counts the row. So this condition is just for row 1 until n minus 1. This is why I just check here, and that's it. Okay. So we have, for a tableau that is a serialization, we have a set of tableau. We can construct this nice set of tableau. This the set of tableau, the set of all serializations, and construct a vector space. Okay, so we have all the ingredients. Then our definition of admissible set of relations. When a set of relations is admissible, if first of all should have a serialization, it has at least one tableau that is a realization for this set and also what we should have here is that for any serialization, this vector space, the vector space we constructed, together with Gelfan setting formulas, give us a model, a GLN model. So this is an admissible set of relations. Okay, nice definition, but do we have, or are we able to describe admissible sets of relations? Actually, yes. Gelfan setting theorem, this Gelfan setting construction or theorem, actually says that if we consider this set and associated with this set, we consider this graph, then this set S should be, so the union should be or is an admissible set of relations because you put any tableau that is a realization for this graph or for this set of relations, then you put Gelfan setting formulas, what you get is a finite dimensional model, simple finite dimensional model. So Gelfan setting theorem says that this is an admissible set of relations. Okay, so we have at least one admissible set of relations. Okay, so natural question. So that was actually one of the first things that appear, like how to go from finite dimensional to another, to some infinite dimension. So how to construct admissible set of relations. So, okay, so assume you have at least, you have a set of relations that is admissible. So you have, what we have is a graph. You have this associated graph. And the idea is we can just look at maximal or minimal points on this graph, right? And associated with this maximal or minimal point, you can go to another graph or another set of relations. We call this Cij. What do we do? We just erase all relations, all arrows going to or connecting with the vertex Ij. We erase all these arrows, and then we produce a new graph or a new set of relations. Okay, so this is, we call this removal relation method, and we say that two sets of relations, one set is obtained from the other by removal relations if it is obtained by a chain of procedures like this, like step by step. You erase one maximal or minimal point, then these two sets of relations are obtained one by the other by removal relation. Okay, so nice theorem. What we have is, if we have an admissible set of relations, you apply this removal relation method. Then what you obtain after that is also admissible. So if you start with admissible set, you remove relations in this way, then you obtain an admissible set. So this is a quite nice way to construct admissible sets of relations. And just an example, very matter example. Okay, so from the beginning, we just note that the relations associated with finite dimensional models, they are admissible. So this graph is associated with some admissible set of relations. Okay, what we can do is This is a minimal, I will call this minimal. This is a minimal point. For one is a minimal point. You can just erase all relations from going or connecting to for one, and then you obtain this new graph. So by the theorem, or by the previous theorem, this is an admissible set of relations. Okay, so we can do the same procedure here, and 3,1 again is a minimal point. So we apply this removable relation method, we obtain this graph. Again, this is a graph associated with some admissible set of relations. And again, this is minimal. We can erase this arrow and this arrow. We obtain this. Again, this is admissible. And at the end, we can consider this, again minimal. You erase the relations or remove the relations, and you obtain this nice set of relations. So after this chain of procedures, what we get at the end is an admissible set of relations. So you can actually construct this. Good. But what we wanted, our goal there was like describe all possible admissible sets of relations. And in this case, what we did was to try to understand all possible graphs associated and check what kind of conditions does they do not produce admissible set of relations. So we start erasing it. After cleaning, what we get is some condition like this. Okay, so this is a nice and important condition. So this diamond condition is, it says like, if you have a pair, so this is connected with the graph associated with the set of relations. So you look at the graph, and you look at two elements in the same row, such that they are connected by the graph, but there is no one in between in the same row that connects these two elements. So this is what we call adjoining pair. It's like two elements, and there is no connection between one element in the same row in the middle. Okay, so what we have to check is that any adjoining pair should be connected in this way, or should be connected by the top row at some point in this way. So this is a nice condition because it depends just on the graph. You look at the graph, and you can say if the graph satisfies the condition or not. Okay. Okay, so the theorem says, okay, if you, let me see. So these first conditions are actually, they appear after cleaning all the sets of relations. Those are bad things that we don't want because we don't get admissible models. So after cleaning, the idea is we have an admissible set of relations if and only if the graph is a disconnected union of graphs satisfying this delta condition. So this delta condition is important. You look at all connected components, and if every connected component satisfies this delta condition, then you have an admissible. And actually, this is an if and only if. Okay, so we have a description. Okay, so some cases that were studied before were like generic models. So the class of all generic models actually can be obtained by this construction. Just consider as a set of relations empty set. Then this construction, where I kind of describe here, will lead us with a construction given by Droz, Obsienko, and Futurni in '94 of the family of generic models. An important thing here is that if you have an admissible set of relations, that means a graph, so the idea is each graph goes to an infinite family of models. So in the same way as finite dimensional case, if you consider the graph associated with the standard set of relations, then you obtain all finite dimensional models, not just one. So this is a nice thing. So this family of generic models can be obtained just considering empty set. And it was studied for a long time. Okay, so also you can construct certain Verma models. Some Verma models can be described in this way by the set of relations with graph associated given by this. Oops. So this is the graph. And they are generic Verma models. Actually, when Maser-Shuk studied this kind of models, what he did was he was studying this construction, the construction of generic models, and inside the generic models, he realized that it was possible to construct certain Verma models. And using our terminology, we can just describe this like diagonals going down. That's very nice. And this is, again, a family of models. Also, we have this Caspidal models. Also, it was studied by Maser-Shuk, and it's quite interesting. So if you look at this piece of arrows, it actually looks like, in the case of finite dimensional models for, or standard for GL4. Then, for this example, actually I take n equal 5. But then this is a Caspidal model. In this case, Caspidal means like dense plus finite dimensional weight multiplicities. And the nice thing is that the finite dimensional weight multiplicities here are controlled by this GL4, finite dimensional GL4 model. So you can see that. So again, we have a family of Caspidal models that can be produced in this way. So it was a nice thing. Okay, so good. We have some models for GLN, but what kind of structure? Are they good models, nice models? Actually, yes, the structure of them, they can, okay, so are they weight models? Are they generalized weight models? Whatever. So the thing is, they are actually nicer. We can construct this Gelfan set in subalgebra, like this is a maximal commutative subalgebra of the universal enveloping algebra that can be constructed in this way. Oof. Okay, it's like union of centers associated with some chain of some embeddings of GLN. So just why do I have to do this picture? Because this Gelfan set in subalgebra depends on the embedding that you choose here. But I am choosing just the embedding through the left top corner. So, and this is called the standard Gelfan set in subalgebra. You can construct this maximal commutative subalgebra of U of GLN. And you also have that the U of H is here. Oops. Important thing is this maximal commutative subalgebra contains the universal enveloping algebra of the Cartan subalgebra. So it's nice. And what a Gelfan setting model is a model that can be decomposed with respect to the action of gamma. So we just need generalized gamma eigenspaces here. And this is a Gelfan setting model. Okay. So the idea is that all models we constructed are actually Gelfan setting models, so they behave nicely with respect to this gamma. So I just need to write this. And also, what we have is that dimension of this space is less or equal to 1. So our models are Gelfan setting models. All dimensions are at least 1. And also, we have this is actually the nicest thing. The action of gamma is semi-simple. We have diagonalizable action of the generators of the Gelfan setting subalgebra. So we have a nice, very nice model here. Okay, so well behaved. Okay, just maybe it's important to mention that actually what we have explicit generators for the Gelfan setting subalgebra, and also we have explicit action of the generators. So it's quite, we know exactly the action. It's just certain polynomials, certain symmetric polynomials with entries inside the Tableau, okay? Okay, so I wanted to talk, actually, the title of the talk was about simple subquotients of these kinds of models. Okay, I did the construction. Now, how can we construct simple subquotients? Okay, so I started with the following. If I have a Tableau, I can associate to this Tableau certain graph. So before a set of relations, I associate a graph, but now start with the Tableau. We can associate a graph. It's just like the graph of all possible integer relations. Yeah, this is kind of what I am describing here. And with the convention, if you have equal entries, then the arrow go down, and if they are different, maybe the arrow should go up. So this is a nice way. Okay, maybe with the example is cleaner. So we have that this difference is greater or equal to 0. So we have an arrow here. This is greater than 0. We have the arrows here, and the difference here is greater or equal to 0. So you have an arrow going down. Anyway, just to remember, to recall actually, that was a realization for this set of relations. It was one of the examples before. This Tableau is a C realization where C is the set of relations with associated graph, this. But now we have another graph. Of course, in this case, it's bigger, but the idea is how these two graphs are related and what does it mean, so what is the relation with the simple subquotients of the model we constructed. Okay, so we have another thing, another definition. Is this associated with any Tableau in the basis of the model? We can construct this set, omega plus, is the set of all these triples such that the difference is greater or equal to 0. Okay, I will just mention that this omega plus of T of L is counting, or no, is related with the arrows pointing down for in the graph associated with the tableau. Okay, so I define a graph associated with any tableau, G of T of L, and I define this set omega plus. Actually, what the relation between these two sets, or the best way to think about this set, is arrows pointing down. That's it, related with. Now, what is the nice thing about this omega plus? I have that. The nice thing about this omega plus. First of all, if you have a basis element, you can describe explicitly what happened with the module generated by this element. So the module generated by this element has a basis, should be like the set of all basis elements, such that you have this we have this relation between omega plus. Okay, so you start with some T of R in the basis, and you consider all tableau satisfying this relation. This is a basis for the module generated by the original tableau. That's nice, okay? And what about if you have a tableau, you can also think about, okay, I want the simple subquotient. So I want a basis for the simple subquotient contained in this tableau. So you will start with this tableau T of R, and the simple subquotient. Okay, what does it mean? It's like you have a tableau, you look at the model generated by this tableau, and then you cut. No. You have this tableau, you think about this model generated by this tableau, and then you cut by the maximal, by a maximal submodule, and then you get a simple subquotient. So the idea is, what should be the basis, or what is the basis of the simple subquotient? Is just the set of all tableau with the same set omega plus. So this omega plus is actually quite nice. It measures the relation, it measures how it works for the simple subquotient, and also for the model generated by a tableau. Okay, so it's, and okay, just one observation here is just this omega plus. If you think about this like arrows pointing down in the graph associated with the tableau, so if you have a tableau and a set of relations, because you have a tableau, is a serialization. Then you have the graph associated with the set of relations, and you have the graph associated with the tableau. What is the relation between these two? This is a subgraph. So any tableau, actually, if you have T of R in the basis, you impose the condition that all tableau should be serialization or should satisfy C. In particular, the graph should contain all possible arrows that appear here. So the graph associated with C, is related with this always. Okay, so as we have this condition, it is enough to look at arrows outside G of C. It's like if you want to study these graphs, it's enough to look outside G of C because all of them, all these graphs, have something in common. So if you want to look at this set omega plus, so this and the conditions are some containment in between sets, so it doesn't make sense to look at the part inside G of C. So we are just looking outside G of C and look what is going on there. So I just want to finish my talk with an example, very short example. To simplify the situation. So what we have is, if you have the graph associated with the set of relations, for me will be, I will consider this. I use this several times. So this is our set of relations. And I consider some Tableau. That should be a serialization for this. So I will consider like 2, 2, 2, 1, 1, 0. And here like pi root of 2, square root of 2, for example. Then in this case, we have like T of L is a serialization. We just check the arrows. That should be okay. And the question is how to describe the irreducible subquotients of the model VC of T of L. Then nice thing about this theorem is you can see everything here. And what we do is, consider the graph associated with the Tableau. In this case, the graph should be like this, maybe this, oops, this, Y, 1, 2, yes, Y, okay. Should be a space in between. Okay. We have this graph, and then what I am telling you is, in order to understand the simple subquotients, you take off the part associated with the set of relations and look at the arrows outside. Then what happened here is, what happened here is that possible omega plus or configurations of arrows. You look at this, and then what you get, if you look at these two connections, you can get something like this. Oops. Or you can get like something like this, or two arrows going up, or down, up. Okay, so you have this, 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 and this. And the idea is that each possible configuration gives us a simple subquotient of this model, of the model VC of T of L. And okay, one thing I may say is maximal possible set of arrows going down means that you have the socle of your model, and okay, so you can actually 1 minute. That you can describe the Lowy series thinking about these sets omega plus. So you can consider maximal size of omega plus are the socle. Is maximal size of omega plus. Then you put some direct sum of modules with, for example, these two modules have just, no, these two modules just have just one arrow going down. That means they are together, like there's one arrow, same size of omega plus. So each level of the Lowy series is described by the size of omega plus. You just put the direct sum of all modules satisfying this condition. And okay, so this is some references. This is the model where we describe these relation models. And in this paper, we actually did all this construction for irreducible subquotients for generic models. That means set of relations equal empty set. That was done there, and thank you. Okay.
So all these modules have a finite Lowy series.
Yes, they have, all these are finite length models, indecomposable finite length models. Yes, all of them. And yeah, the Lowy series is completely determined by this. So
they could not be semi-simple.
They are not.
More questions? So we have a coffee break now, and let us thank Enrique again.
Thank you.
We start in half an hour.